Did it work out? Lambda n? What? Oh, the second expression, correct. So you can use the second expression and choose. Yeah.
Of n within the whole space.
Exactly. Exactly.
So maximum overall is.
Correct. Does everybody see that? So if you use this expression, you get lambda n easily because you're varying over all s of dimension n, but that's just one thing, the whole space. So that minimum is not important. So it just ends up being the maximum over the whole space of this expression. Okay? So that's where those two come from. And the next one is just the eigenstructure of the complete graph. Okay? So if you're not familiar with that notation, so Kn means the complete graph, and this has vertex set n, and the edge set is all possible edges. Okay? So you choose all possible two-element subsets of 1 through n. So for example, if we do K4, you have 4 vertices, which are numbered 1, 2, 3, and 4. And then we have to allow all possible edges. So 1 is connected to 2, and 3, and 4. 2 is connected to 3 and 4, and 3 is connected to 4. So that's the complete graph on 4 vertices. In general, you have a complete graph on n vertices, right? So it'll have this choose 2 edges. That means altogether, so the number of edges is going to be n choose 2. Okay, that's the number of edges. So that's the biggest graph that you can have on n vertices. Okay, so for that one, you have to first write down the Laplacian. Is that okay? Does everybody see what does the Laplacian look like? So let's put it somewhere. We'll put it here. So L of the complete graph, the Laplacian, should be the degree matrix minus the adjacency matrix, right? So the degree matrix is exactly minus, how does the adjacency look? Exactly. So you have zeros on the diagonal, but everything else is 1, like that, right? And now, do you see you can rewrite it as Ni minus J, which is the full all ones matrix. So you can rewrite this as Ni, that's the first piece. And then you combine the minus I with the adjacency. So this becomes J. J means the matrix that's filled with ones. You know, ones everywhere. That's J. Okay? Good? Okay, so that's a Laplacian. And then you got to argue what its eigen. So what are the eigen? Okay, let's do this one. So what are the eigenvectors? Eigenvalues of the identity. Yeah, so what the identity will do to any vector is just give you back the vector, right? This is true for all v. So then the only eigenvalue is 1, but it's repeated n times. So these are the eigenvalues of the identity. And the eigenspace, there's only one eigenspace, which is all of Rn. Okay? So that one is good. How about J? 1, how many zeros? N minus 1, yeah. So this is a rank 1 matrix. So its null space is n minus 1 dimensional. So this one has eigenvalues 0 forever and then a 1. N minus 1? N, sorry, yeah. And then you kind of have to put it together and you'll see what the eigenvalue of Ni minus J is. Okay? So that's just linear algebra. You know the eigenvalues of Ni, it's going to be n, and J is going to be 0, 0, 0, n. Okay? So you put it together and you get that. So we're going to need both of those results. Okay. So in the afternoon, what I want to do is to show you why people care about eigenvalues and eigenvectors of matrices associated to graphs. Okay, there has to be some use, right? Ideally, there has to be a use. So, of course, there are some people here who know spectral graph theory who don't need any motivation. But for the rest of us who might want to know why is this useful? Why do we care? And the whole point is simply that the eigenstructure of these matrices can give you a lot of information about the graph. Okay, so let's do like 3 of the kind of big greatest hits of spectral graph theory. Okay, so we'll do 3 results. They're very common results, so if you've seen it before, then be patient. But let's start with the very first one, which is how to detect connectivity from the eigenvalues. So the first result is this result that says that G is connected if and only if lambda 2 is positive. Okay, so these, remember, lambdas are the eigenvalues of the Laplacian. First eigenvalue is 0. So the second one, it's sometimes called the Fiedler value. This lambda 2 is called the Fiedler value. It's also sometimes called the algebraic connectivity of the graph. It's a very important number. It's related to things like expansion. Lots of people study the second eigenvalue. And the result is that G is connected if and only if the second eigenvalue is positive. Okay? So that means the null space of the matrix, which is the first eigenspace, has to be just one-dimensional, right? Does everybody agree with that? So if I take L, let's put it here, L, then the kernel of L, the null space of L, these are all the x's such that Lx is equal to 0. Okay? This is, so definitely the all ones is in here. So this contains the span of the all ones, because we know that L times 1 is 0, right? We know this. So the all ones is in there. And this null space is the eigenspace of 0, the eigenvalue 0. Okay, so the first eigenspace comes with the eigenvalue 0. It's the null space of L. And what we're saying here is that connectivity happens only if lambda 2 is positive. That means the first eigenspace, which comes with eigenvalue 0, can only be the span of 1. Okay, it can only be, if you have equality here, then you have the span of 1, which is some line, and then everything else is orthogonal to that, right? So this kernel has to be exactly that. That's what this result is saying. Lambda 2 has to be positive for the graph to be connected. Is that okay? All right, so the null space of L is the same as the eigenspace of 0. So that's a little piece that's important. Okay, so I think we're going to do this proof together. This is a very easy proof. So let's actually argue that this works. Okay, so G is connected if and only if lambda 2 is positive. All right, so what do we really have to show? We have to show that the multiplicity of 0 is 1. Do you agree? So lambda 2 being positive is the same thing as saying that the multiplicity of the 0 eigenvalue inside L is 1, right? So we're going to start in lambda 1, which is 0, and then comes lambda 2, and we're trying to argue this, right? Strictly positive. So that means this one better only happen once, right? Otherwise, lambda 2 will also be 0. So showing that lambda 2 is positive is the same thing as showing this, okay? But that's the same thing as showing that the dimension of the first eigenspace, the eigenspace of 0, is 1. Is basically the span of the all ones vector, right? So this is basically what we have to do. So connectivity happens only if the dimension of the first eigenspace is 0, but the first eigenspace is the null space of L, right? So we're arguing that the dimension of the null space of L, which is the nullity of L, right? Dimension of null space of L is 1. Okay? This is what we have to do. Everybody okay? So what we need to do is take L and argue that there's only one element in the kernel of L, right? So otherwise it's not going to work. All right, so this is the work we got to do, okay? All right, so let's start by assuming G is disconnected. So suppose G is the union of a bunch of graphs. Let's say. okay? So it just means there's a piece here, then there's a disconnected piece here, there's a disconnected piece here, and so on. So it's just a disconnected graph, right? Okay, so then we already had the question from, what was your name? Sudhakar. Yeah, so Sudhakar already told us what happens when G is disconnected, right? What happens to the Laplacian? Yeah, so the Laplacian of G is just, it's a square matrix. In this block, you will see the Laplacian of G1. If we arrange the vertices so that all the G1 vertices are first, then all the G2 vertices are second, and so on, there we'll see the Laplacian of G1. Here we'll see the Laplacian of G2, all the way to the Laplacian of GK. Right? Everybody okay with this? So some people write this as a direct sum. So you write this as LG1, direct sum LG2, direct sum, like that. Okay? Maybe that's not so important. Okay, anyway, it's this block diagonal thing. How big is the kernel of this? The right kernel. Can you start sticking things into the kernel? Do you see some vectors that have to live in the kernel? Can you produce k independent vectors in the kernel? Yeah, what do we do, Kranta?
So first G1 number of vertices you take one, that is the series.
Okay, so Kranta is saying that you go to the length of G1, so this is the vertex set of G1. You put ones here, right? That's what you want. And then zeros everywhere else. This is certainly in the kernel, do you agree? Because it'll annihilate it's in the kernel of LG1 and everywhere else it has no effect. Okay, so then how many do we produce like this? Yeah, so we can produce all the way to this one. So let's call this V1 up to Vk, okay? So they're all in the kernel. So if I do LVI, I will get 0 for all I from 1 to k. Good? Okay, so that tells you the dimension of the null space is at least k, right? They're independent, you agree they're independent? These k vectors, okay. So we have that the dimension of the null space is, which is the same as E0, is at least k. E0 is the null space of the 0 eigenvalue, okay? How do we prove it's exactly k? That's what we need to do, right? Okay, we're going to prove something more complicated, I guess. We're going to really prove that G has k components. If and only if lambda 1, lambda 2, all the way up to lambda k is 0. Okay? We're really going to prove this. So if we can prove this, do you agree that this works out? Yeah? So if G has only one component, then only lambda 1 can be 0. Okay? So we're actually trying to prove this. So this is the same thing as saying that the multiplicity, or rather the dimension of the 0 eigenspace is k. This is the same thing. Okay? So we've just argued that the dimension is at least k. Good? So how do you think we can argue that it is exactly k? There's nothing more in the null space.
So you take the span of these two vectors and take something to the orthogonal complement of that span.
Okay.
And check that it doesn't belong to the null space.
Okay, yeah, that's a good idea. We could do that. We could take this, take something in the orthogonal complement, and then check that that doesn't do what? It's not in the null space. Correct. Okay. Another thing we could do, which is exactly the same idea, is to pick something in the null space and argue that it's in the span of these. Okay. So can you try that? Let's pick something in the null space. It's the same idea. Okay, so pick a V in the null space. So this means that LV is 0. Okay? And now your job is to argue that this V is made up of some combination of V1, V2 up to Vk. Then that's also same. It's the same idea as we just heard. Okay. Can you use something we learned? Like with the quadratic form, maybe? Okay, let's try to squeeze the quadratic form into this, okay? So if LV is 0, what can you say about V transpose LV? Also 0? Okay, so this is also 0. But now can you rewrite it in terms of those edges, square and all that, sum square? So let's try it. So this means this is the sum of Vi minus Vj square over all edges. Okay? So this sum of squares is 0. Good? So what can we say about Vi minus Vj? Yeah. Exactly. All those squares are 0, right? So exactly. So this tells you that Vi equals Vj for all edges. Okay? Vi equals Vj for all edges. The two values on two sides are the same. Yeah, so then what happens if you have a graph? So I start somewhere and I get a value, some value, I don't know, alpha. I go across to a neighbor, it's also alpha. This is the V value, okay? And I go across, it's also alpha because all the edges are alpha. Come back here, it's also alpha. And then the only way it can change is if I take something that's not connected to this piece, right? So if I have another piece of the graph here, this will all be beta, 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 beta. That's okay. Do you agree? That's kind of how this thing has to look, how V has to look. So then do you see we're done? So we want to argue that this means V looks like something V1 plus something V2, right? Because in each component, it's like the same. So it's a multiple of 1s with 0s at the bottom. Questions? Does it make sense? Yeah? Okay, good. Okay, so this is like the most basic result in graph theory, in spectral graph theory, okay? That the connectivity comes from just looking at lambda 2. So you don't need to check, like if you have, a million vertex graph, linear algebra can do million by million matrices, not a problem. Okay, you just feed it into some industrial strength linear algebra solver like Julia or whatever, Python, I don't know. And it'll tell you the eigenstructure. It'll tell you the eigenvalues. So I don't need to go check this graph to see if it's connected. I just look at lambda 2. If it's positive, we're done. The graph is connected. Okay? And it's actually this more stronger result that if you want to know how many components there are, you just look at how many of the first eigenvalues are 0. That's pretty nice, right? So this is one immediate use. And in fact, the bigger the lambda 2 is, the more connected the graph is. That's why it's called algebraic connectivity. Okay? So if you have internet, you can Google for this algebraic connectivity, and you'll see like people have plotted, they've taken, large numbers of graphs, and they've like looked at how many, so fix the number of vertices. So let's say you fix 5,000 vertices, and just start putting more and more and more edges, and make a plot between lambda 2 over here, and the number of edges over here. So you have to fix the number of vertices to something. Let's say 5,000, okay? So as you have more and more edges, you'll see lambda 2 increases. Did I get it wrong?
Yeah.
Oh.
Edges are your independent variables.
Oh yeah, edges are independent variables, sorry. Yeah, lambda 2. And so you'll see like some sort of graph like this, okay? You can Google for this. It's not like a nice shape, but it's generally going up, okay? So this is why it's called algebraic connectivity, because it's the more lambda 2 is, the more you want to. So Thursday, I think, we'll talk about how you maximize lambda 2. Why would we want to maximize lambda 2? Like, let's say you have a graph and you want to know, okay, if you want to change lambda 2 on a graph, you have to start putting weights on the edges because the graph just comes with one lambda 2, okay? But if you allow weights on the edges, lambda 2 can increase or decrease, okay? So for example, if you put 0 weight on some edge you already had, lambda 2 will probably decrease. But if you start putting more and more weights on the edges, it'll increase. And on Thursday, we'll see an example where why people do this, okay? Why it's good to know what's the maximum lambda 2 I can have on a fixed graph. And this is very important. Like, for example, you may have like a fixed infrastructure, like you have some electrical network that's already under the ground. You don't want to dig this up, but it's available to you to change the capacity or resistance or something on the various pieces of this electrical network. So you might want to know, how can I make electricity pass through this as quickly as possible? And that is the problem of maximizing lambda 2. Okay, this has a lot of interesting applications. So for example, if you want the fastest Markov chain on a matrix, if you want information to spread super fast through your graph, like a social network, for example, you want to know how diseases spread across countries, like how did COVID spread? If you look at which countries are connected to which countries by airplanes or whatever, you want to know how fast this moves, it's a function of lambda 2, okay? So you might want to sometimes increase lambda 2, sometimes you want to decrease lambda. I mean, decreasing is easy, you can just cut the graph, it'll decrease to 0. But increasing lambda 2 is actually a serious problem. And there's a lot of people who worked on it, including like Diaconis and Boyd and all these people, like, maybe 20 years ago. There are papers on this. So we'll come back to this later. So this is lambda 2. So lambda 2 is really important. So that's the first application. So now let's talk about clustering. No, I don't think I have anything to show on the computer with lambda 2.
You can show that fielder vector.
Yes, so it'll come up in clustering in a minute. Okay. Then we'll stop and do a lot of computers. Is this okay? Everybody got this? Okay. Okay, so now I'm going to do another application, which is graph clustering. And for this, there will be a few times we have to stop and look at pictures and also do exercises. Yeah, so the eigenvector of lambda 2 is called the Fiedler vector. There may be many eigenvectors, because it may be a multiplicity, it may be a fat eigenspace, but any one of them we call the Fiedler vector. Okay. Oh yeah, then maybe we should show the picture of the Thomason graph that you noticed, right? Okay, yeah, let's do that first. That'll be good. Okay, so the next thing we want to know is how to partition a graph into two parts, so that there are very few edges that go between the two parts. So it could be that naturally your graph has, lots of people here, and then lots of people here. So this may be like all your friends who do yoga. Okay, that's some community, right? So this is all connected to each other. Everybody's friends with everybody. This may be everybody who does something completely different, like, I don't know what. What? What? Gym. Gym and yoga are kind of related, right? But no?
Music class.
Music, okay, music. Let's do music. So these are all the people who can sing. And this is another group of people. And maybe not, maybe some people who do yoga do music. Okay, let's find something else. But still, maybe not so many connections. And another one. Okay. So computer nerds. Okay, maybe computer nerds also do yoga. I don't know. They probably need to do yoga. So anyway, there might be some situations where there are only like a few connections between the communities, right? And you often want to know how do you catch the big clusters in the graph. And this has a lot of uses too, because you might want to know like how to advertise to these clusters, right? Like the people who do yoga may not care about, the latest Mac model or something, but the people who do, and so on. So it's kind of good to know. So this is not a disconnected graph. It is connected, but there are like very few edges between groups sometimes, and you'd like to know how to actually find these clusters, okay? So this is very important. And Arvind just pointed out to me that we already saw this in the picture that we had before. So let's see if we can see it. So down in your notebook, there's this graph, okay? So it's called the tadpole graph. It's in the same notebook a little bit later. So this graph is, I just picked a small graph. Do you obviously see the clusters in this graph? Like if you had to cut this graph somewhere where there's like a weak connection, where would you cut it? Like this center one? This one? Yeah?
I think you have to tell them that you're cutting edges, not vertices.
Yeah, we're cutting edges, right? So when we're clustering, we're just trying to have, basically if I erase these edges and these edges and these edges, I will disconnect the graph into big clusters, right? So I want to cluster this graph. This is a very small graph, so it's a little bit not maybe entirely clear, but the three things in the triangle, they're very well connected, right? So you kind of probably want to keep them in one cluster. And what else should we do? We could try to keep these two together and remove this. That would be a cluster. Is that like the most normal one? Like the most natural one, you think? Yeah, if we cut this, it's a little less natural, right? Because we are just allowing this little edge to poke out of the triangle and then one vertex is isolated. It's a clustering, but maybe the first one that you wanted is the most natural. Okay, so this is how you do it. This is like a basic algorithm to do it. We compute the Laplacian of the tadpole matrix, okay? This is called the tadpole graph. Compute the Laplacian. Here are the eigenvalues, which are numerical, which is fine. Here is 0, and here is lambda 2. Okay, so 0.51, a little bit bigger than 0. Okay, so it's connected. And now what we're going to do is, then I got all the eigenvectors. Okay, fine, I got the eigenvectors. And then I'm going to look at, okay, what is this? Yeah, I don't want to do that so much. Okay, so let's just look at these eigenvectors and look at the eigenvector corresponding to lambda 2. It's this one. Can everyone see this one? Okay, so now if you choose, so if you look at this carefully and you look at the graph and your proposed clustering, you see that the triangle corresponds to all the negative guys and the other ones correspond to the positive entries, okay? So this is a basic algorithm. You can take the second eigenvector, and everywhere it's positive, you put into one cluster. Everywhere it's negative, you put it into the other cluster, okay? Why should it have both positive and negative entries? Is it guaranteed to have both positive and negative? Because? Exactly, okay? Correct. So the reason is exactly that the second eigenvector, and in fact every eigenvector after the first one, is orthogonal to 1, 1, 1, 1, 1, right? So that means when you take the dot product, it'll be 0. That means the sum of the entries have to be 0. So there has to be positive and negatives in it, right? It can't be all positive or all negative. You cannot get that. So they're guaranteed to be negatives and positives. Maybe some of them are 0. That's okay. And if that's the case, you arbitrarily decide where you want to send it. Either you send it to the plus group or the minus group, okay? So that's really the basic algorithm. You take this eigenvector and you just take all the vertices with negative coordinates into one cluster and everything with positive coordinates in the other cluster. Okay?
There's an underlying theorem here, this Friedler's theorem. It says that all of them will be connected. The negative ones, a priori, we don't know.
Oh, that's true. That's true. I see. Okay, so maybe we can think of, okay, so that's something to think about. Okay, so this is just an algorithm. And in Mathematica, there is this command called community graph plot. So it's some proprietary algorithm they use, and it'll just find communities inside graphs. And it exactly cut it the way you said we should cut it, right? So it switched the tadpole graph, it mirror imaged it, but here's the triangle part, and here is the other edge, okay? So you can do this. And if we had done this for the Thomason graph, this graph, which is like a bigger graph, and this was the second eigenvector, okay? Do you see the clustering happening? So the red and blue are probably positive and negative, okay, kind of. I mean, they're at least very different from each other. And you see that it's clustering one side and going to the other side, right? So that's exactly one heuristic way to do clustering. And we'll talk about how to do the best thing, which is NP-hard. It's really hard to find the best clustering, but there are these approximations, and this is a good approximation, okay? So here you see, right, like the red things are getting split off from the blue things. In this graph, it's not so clear exactly what to do, but it seems like it should be roughly in the middle that you should cut. It seems like a pretty symmetric graph, right? So it seems roughly correct. But then if you ask Mathematica to do multiple edges, you're allowed to cut multiple edges, but as few usually, okay? But I'll define this more carefully. But if you ask Mathematica to do it, this is the picture it gives you. This is cutting into K clusters, okay, not 2 clusters. So you can ask Mathematica to give you K clusters, for example, and this is what it gives you. Okay, this looks nothing like the other graph that we just looked at, right? But it's the same graph, just embedded differently. Good, so it has some algorithm that it's actually using, but there's a linear algebra algorithm that we will look at. Is this okay? So this is the idea of clustering. All right, I think that's all we need this for. Oh yeah, then it'll also do things like, it'll tell you the clusters, so it's telling you that, okay, this first group of vertices, 16, 17, all the way to 94 is in one cluster, then there's another cluster, and so on. And it'll also, you can make it show you, for example, the second cluster, okay? So the second cluster is here, this one, and it's exactly this piece. Okay, now we're cutting into K clusters, not 2 clusters, but it'll actually show you where the cluster is.
I'm confused. Your command did not have any K in it. It naturally chose the K?
I think it's 2, see?
No.
Oh, it naturally chose, yeah, I think it does something weird. You're right, in the beginning, right?
Yeah, you did say that.
Yeah, I think it just does like what it thinks are the natural best clusters inside this graph. Yeah, we don't exactly know how this works, so it's just a command. All right, so that's it. That's the picture. So now let's actually look at, how do we go? 3:15, okay. Let's look at the theory. Yeah, like we can switch it off. I mean, I do want to show, yeah, we can switch it off because the clustering is going to take a while. So there are different ways to do clustering, and this way of doing it today is using spectral information. That's why it's called spectral clustering, okay? You can do other things. So as we said, what we're trying to do, so we're just trying to cut into 2 clusters. So I want to take my graph and create 2 clusters like this with a few edges that go across it. Okay, this is the picture. So inside here there are lots of edges, inside here there are lots of edges, we don't know, it's just 2 black boxes. But in the middle we want to minimize the connections, okay? So we want to say we cut it off there, it's okay. And this is used for lots of other things too, right? Like if there's an earthquake and you want to know which communities will get cut off from other communities, it's a road system, like the graph is a road system. And you can see where the weakest links are, right? So maybe like you'll cut off this mountainous community from this other mountainous community because the roads just collapse. So it's really important to know where these weak links are. Or, you know, internet communication, same thing, like where if the power goes off in one particular place, what's like the worst place that'll cut communication across? So many uses for these things. Okay, so let's call this cluster S, and let's call this cluster, this is everything else, so I'll just call it S bar. Okay, so S bar is just N minus S. Okay, so those are the two clusters. And then I'm going to make a few definitions. So we can say a cut in the graph is a partition of the vertices into some set S and its complement. Okay, so this is a cut. So it's just a partitioning of the vertices into two parts. Neither part should be empty, I guess. So you definitely want to make sure that S is not the empty set, because otherwise you just get the whole graph back. And you want to make sure that this is not everything, right? So we want only the proper subsets of N, and we're going to call a cut just a partition. Okay, so if I tell you the partition, that's enough, right? Because then you can just look at which edges go between the two. I don't need to actually list all the edges, I just need to know this is one part, this is the other part, and if you need the edges, you go find the edges, okay? So we're gonna call this a cut. Okay, so let's let the edges that go from one side to the other side have this notation. So these are the edges, so these are the ij's in the edge set, such that I is in S, and J is in S bar. Okay, so that's exactly this stuff. These edges, that's this. Okay, so it's an edge set. All right, great. So now I want to somehow parameterize, or I want to kind of quantify what it means to be a weak link, okay, like a weak cut. So we're going to introduce a quantity that I'm going to call phi of S. So S is one of these proper sets, okay? And what I want to do is I want to count how many edges go from S to S bar. Okay, that's the size of the cut, okay? But I just want it relatively, like I don't want to know if there are 100 edges here when there are altogether only 101 edges. It's more impactful if there were 100 edges in the cut and there were 2,000 edges in the whole graph, right? So we're going to take a ratio, we're going to divide this by the size of S times the size of S bar, okay? What is that doing? Do you see what that's doing in the bottom? So this is a ratio. I'm counting how many edges went across, but I'm dividing by the size of one side times the size of the other side.
Size is the number of vertices, right?
Correct. Size is the number of vertices in S and in S bar, right? Do you see what this could be? Like, what is this counting in terms of edges?
All the edges that could be between the parts.
Exactly, right?
Maximum.
Exactly. So this is the maximum number of edges that could have been between S and S bar, right? So this is the ratio we're interested in. So this makes some sense, right? Because it's a relative quantity.
It's between 0 and 1.
Exactly. It's between 0 and 1. So this ratio is between 0 and 1. But, so in computer science, people do different things. For today, we're going to multiply this with an N, okay? N is just a constant. It's the number of vertices. And this quantity is called the cut density. It's called the cut density of S. So it depends on S. So this is called the cut density of S. Okay, so depending on what you're studying, this thing looks a little bit different. If you've studied expansion, you're doing something slightly different. There may be no N, or you're dividing by other things. It doesn't matter. They're all roughly the same. Okay, so for today we'll study this. Does this make sense? So this we're going to call the cut density of S. And what we want to compute is phi of G, which is the minimum of phi of S. Okay. So I want to go over all possible S's and calculate the minimum over all proper subsets inside the graph. Okay, so this is a definition, and we call this, okay, I'll say that in a minute. Everybody okay with this? So I go over all possible S's and calculate the minimum of this ratio. Okay, we call this phi of G. And then the main definition is that a cut with phi of S equal to phi of G is called the sparsest cut. Is the sparsest cut. Can you see this color? Yes. In G? Okay. Okay, so this is a definition. So we're going to look for the cut in G, the S, that achieves the minimum of all of these phi of S's. Good? Okay. So a priori, how much calculation goes into this if we had no method? Yeah, it's terrible, right? You have to compute all the subsets of n. You have to count how many edges go through, then you might as well just end at the end of that, right? You have the sparsest cut because you've looked at all possible S's and so on. So this is an exponential amount of work, the way it's defined, right? So what we're going to see is, and computing this is NP-hard. So finding the sparsest cut in a graph is NP-hard. If you can do this fast, then P equal NP, you get $1 million, all that kind of stuff, right? So what we'll see are some approximations. So we'll see how to use eigenvectors to approximate this phi G, okay? All right, so
What is the name sparsest?
it's the sparsest, right? It's like the most sparse.
Minimum number of edges that would require between the dots.
It's not the minimum number of edges.
No, it's
Smallest number.
It's the S for which this is the smallest, this ratio.
Intuitively, it's like you want to minimize the number of things you're cutting.
Exactly. So you are actually ending up cutting very few edges. So it's like the sparsest, the cut. That makes sense? Okay. But we're computing with this quantity.
It has nothing to do with the sparseness of the graph.
No. This is really, you're looking at ways to partition the graph with as few things going through the middle, okay, going across. Make sense? So this is the sparsest cut, okay? So this is NP hard to compute, and algorithm 1 is the algorithm we just saw, right? You take the Fiedler vector, so what is algorithm 1? Let's put it here because it's not so important. So algorithm 1, for approximation, okay? So this is an approximation algorithm, which is what computer scientists like to do. When you have a hard problem, you approximate it. The approximation better be easy, otherwise there's no point. So that has to be done in polynomial time. So the approximation algorithm is the one we just saw on the computer, right? So what you do is you compute phi2. So find phi2, and then let S be all the indices where phi2 of I is positive. This is the algorithm, okay? So you look at the second eigenvector, look at all the places where it's positive, put all those indices into S, everything else is in S bar. Is that okay? This is what we just saw, right? So in the tadpole graph, for example, the phi2 had negative, 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 and then positive, positive. So it will say, and the tadpole graph was like this. So it'll say these three guys correspond to this. That is the S. So this is index 1, index 2, index 3, 4, and 5. And this is 4 and 5, and these go into 1. Okay? So this is algorithm 1. Everybody okay? So this is very easy. Do you see what this is doing in terms of, yeah?
So second smallest, I think that you have multiplicity mode, right? So which eigenvector would you choose?
Any. Pick any. Pick any eigenvector of that eigenvalue. It could have multiplicity. So a lot of graphs that appear like in nature randomly and so on, they don't have a lot of multiplicity. Okay? It's these highly structured combinatorial graphs that are fat, like the complete graph, right? It has only two eigenvalues, one eigenspace is n minus 1 dimensional, the other one is 1 dimensional. If you start taking things like random graphs, or you take graphs that come from geometry, then typically there's no multiplicity, okay? It's very rare. But when you have structure to the graph, you see multiplicity. But we have to deal with it because, it's life. So you got to deal with that, okay? Okay, so let me also show you one more, point out one more thing about this thing, okay? So the way the algorithm works is clear? Okay, so what we're actually doing is we are taking, let me try a picture here. So what we're doing is we are taking the real line, okay? And then on that real line, we are plotting the different coordinates of phi2, okay? So let's make up some numbers here just to be easy. So maybe this is -5, -2, -10, and this is 1 and 2. Okay, I'm just making up some numbers. They don't add up to 1, sorry. Okay, 0. Yes. So what you're doing really is that you're embedding the graph using these numbers. Okay, so -5, so let's say 0 is here. So -5 is where you put vertex 1. Then -2 is where you put vertex 2. And then -10, which is way out here, is where you put vertex 3. And then 1 and 2 is vertex 4 and vertex 5. So we are kind of embedding the graph on a line. This is called a spectral embedding because we're using an eigenvector to embed the graph. And then you draw all the edges in. Okay? So I first place all the vertices, and I know the graph is this. So if this is 1, 2, 3, 4, and 5, I know that 1 and 3 are connected. So 1 and 3 are connected, and then 2 and 3 are connected, and then what else? 1 and 2 are connected, but then also like 3 and 4 are connected. So 3 is connected to 4, and so on, right? So you just draw all these edges in. And then what this algorithm, what it's doing, it's just looking at the piece that crosses 0, right? It's looking at all the positive guys go to one cluster, all the negative guys go to the other cluster. So you can see the cut. All we're doing is we're cutting everything that crosses 0. That is the cut. Okay? So it's a spectral embedding on a line where you just look above 0 and say, okay, if an edge crosses me, I cut it off. That's my cut. Good? Okay, so these spectral embeddings will also come back on Thursday. That's why I just wanted to show you the simplest kind of spectral embedding, just on a line. Questions? Is this okay? Question? No?
Explain the second one more time.
Which piece?
How the first algorithm.
Oh, the first algorithm. So the first algorithm is just, first you find phi2, the second eigenvector, any second eigenvector that goes with lambda 2, okay? And then you look at it has some coordinates, right? It has some minus coordinates and some plus coordinates. It may also have 0. So you take all the places where you see minus and put it in one side of that's your S, right? And the rest are in the other side. So that's the algorithm. I'm taking all the indices where phi2i is positive and then calling that S. So the rest is S bar. Is that clear? After that, okay. So then I'm saying that what it's actually doing is embedding the graph on a line. So we're using these numbers that you see as the coordinates of phi2 to place the vertices. So at -5, you will put vertex 1. At -2, you will put vertex 2. -10, you will put vertex 3. 1, you'll put vertex 4. 2, you put vertex 5. Right? But then you have to draw all the edges in, because the edges, I draw them as arcs so that you can see them. So when you're clustering like this, where you take all the positive guys and put it into S, what you're doing is you're looking at the edges that cross 0, right? Because you're looking at everything that goes from the positive side to the negative side. Those are the edges that are in your cut that go between the two sides. Good? Okay, so that's that, okay? So this is the basic algorithm. But now let's do a harder algorithm, and then we're going to analyze it. Okay. Okay, so let's start at least. So before I can give you the next algorithm, so I'm going to define a new thing. I'm going to define a function that looks like the Rayleigh quotient, but it's not. It looks closer to this cut density. Okay. So you take the Laplacian of your graph, that is L, and then, so up here you have the quadratic form from the graph, down here you have the quadratic form from the complete graph, okay? And then there's that n is still there. So this is not this quantity, This is not this quantity. It is not the Rayleigh quotient, but it looks similar to both, okay? So it's a rational function, right? Upstairs I have a quadratic function, downstairs I have a quadratic function, so ratio of two quadratics, okay? So we know what this is, right? We know that this is equal to n times the sum of xi minus xj square over all ij in E. This is my graph. And then downstairs I have sum of xi minus, I want to do it for the complete graph. But now I have to take all possible edges, right? So I have to let 1 less equal to I, less than j, less equal to n. Is that okay? So we know that the quadratic form looks like this. I'm just doing my graph in the top and the complete graph in the bottom. The indices are different, but it looks the same. The expression looks the same.
So we want to make sure that the x is not a constant here.
Exactly. So very important that the x is not 1, 1, 1, 1, 1 or a multiple of that. Do you agree? Otherwise the denominator is going to be 0, right? So the domain of this is only, so this is only defined for x perpendicular, no, let's just say x not constant. So not constant means x is not a multiple of the all ones. That's what not constant means, okay? So every entry should not be the same. If every entry is the same, then we don't have a denominator. Good? So it's a function that's defined for this. Okay, so now we're going to compute this thing, okay? This thing, using this function, okay? So I claim the following. Oh, let's do the following thing. So I'm going to pick an S. So it's always proper, so I'm not going to write that all the time. So pick an S. And this S, so what is this? This is a subset of n, right? 1, 2, 3 up to n. This S has a characteristic vector, or incidence vector, some people call this. So it has a characteristic vector which we will call chi of S, okay? And this is just a 0, 1 vector. So first of all, it belongs to 0, 1 to the n, okay? So it's a vector filled with zeros and ones. And what it's going to do is in the ith position, it's going to put a 1 if I is in S and a 0 otherwise, okay? So it's just going to record the things that are in S. Everybody all right? So example, let's do a quick example. So if S is equal to 1, 3, and this is living inside 1, 2, 3, 4, then the characteristic vector of S, we look which guys are in S, right? 1 is in S, so I put a 1 here. 2 is not in S, so I put a 0 there. 3 is in S, so I put a 1 here. And 4 is not in S, so I put a 0 here. Okay, this is the characteristic vector. It's just a recording of the set. Good? Okay, so this is a 0, 1 vector. And so I can do this for all these S's, right? So can you compute what happens? So this is definitely not a constant vector for a proper set. Do you agree? If S is a proper set, there's definitely some zeros, definitely some ones. So it's not a constant vector. So I can stick it into this QX. Can you see what happens if you do that? Can you compute Q of chi S? Just have a go at it. See what happens. I promise you it'll be worthwhile. So this function evaluated at chi S. So I'll write a little bit here. So it's n. Well, you can probably look at this and see what's happening. So the n is there. That's not going to do anything. What do you think is going to happen to the top part?
E of S is bar.
Yeah, so remember S and S bar are like in that picture, right? So if I stick in the characteristic vector of S, then there are two types of edges, right? There are edges that go inside S, there are edges that go across S, from S to S bar, and there are edges inside here. These are the 3 types of edges there are, right? So if you take an edge that is inside here, like an edge like this, okay, then both these values are 1 in the characteristic vector, right? So that means they'll cancel out here. If I have an edge like this, there's no contribution to that sum square. If I take an edge like here, what happens? Same, right? Because it'll be 0 and 0, doesn't contribute. So the only thing that can contribute are edges that go across, right? So if they go across, then on one side is a 1 and the other side is a 0. It doesn't matter which side because we're squaring. And you'll get a contribution of 1, right? So in the top, what are we counting? I think we just got the answer from Lavanya. Yeah, so in the top, we're getting the number of edges that go across. So this will be n times the number of edges that go from S to S bar in the top. And in the bottom, what are we getting? Do you see? Yeah, so in the bottom, we're doing the same thing, but on the complete graph, right? So we're going to be getting all the edges that go across from S to S bar, but in the complete graph, we're going to get all these guys, right? And we already sort of thought about this, right? How many edges will there be from? It's just the product of the size of S and the size of S bar, right? That's all the edges that can go across. So in the bottom, I'm going to get the size S bar. Okay? And this is exactly phi of S. Phi of S is over there somewhere, right? That's exactly phi of S. So this quadratic function is telling you that if I know all the S's and I calculate all their characteristic vectors and I plug it in, I will be able to calculate each of the phi S's. Then I can take the minimum. We haven't decreased the amount of work, but it is a slightly different way that's going to give us an edge into the algorithm. Is this okay? It's some function. If you evaluate it at chi of S, we're good, okay? So then the big theorem we're going to prove is the following. We're going to argue. So let me give you the algorithm and then maybe we can stop and then we'll come back to it. So it's the second approximation algorithm. It's very similar to the first, just a little bit more sophisticated. So what we do is we first find phi of 2 and then we sort phi of 2 in descending order of coordinates. Okay? So phi of 2 is some vector, and I'm just going to, let's do an example maybe. So let's keep an example on the side here. So example phi of 2 might be 1, minus 1, 0, 0, minus 1, 1, 0, 0, 0, 0. Okay, that's some phi. This is actually the phi of 2 for the Peterson graph. Okay, this is the second eigenvector of the Peterson graph. Okay, so this is a phi of 2, and then every number here comes with an index, right? This is the first, this is the second, third, fourth, and so on. So I'm going to sort them in decreasing order. So what that means is that I'm going to write, so this is, let's put the numbers here. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? So sorting means that I look at the biggest ones. The biggest ones are in the first position and the sixth position, right? So we have phi 2 of 1 is greater or equal to phi 2 of 6. Yeah, those are the top two. It doesn't matter which one you put first, but I have ordered, so these two are done. And then you have to do all the zeros, those come next, right? I'm sorting the coordinates in descending order. So I'm just going to use what we see here. So I can do phi 2 of 3, phi 2 of 4, greater or equal to phi 2 of 7, greater or equal to phi 2 of 8, greater or equal to phi 2 of 9, greater or equal to phi 2 of 10. And then finally, I will get the two minus ones, which are phi2 of 2 and phi2 of 5. So this is what we mean by sorting. Okay?
Sorting is 1, 6, 3, 4.
Yeah, so the sorting is 1, 6, 3, 4, 7, 8, and so on. And there are lots of ties. I just broke them arbitrarily, right? There are a lot of ties. There were lots of zeros, lots of minus ones, and so on. Okay? All right, so this is the first job. And the second piece, so this is the first. And the second piece is to let Sk, so we're going to create a series of S's, and we're going to pick the best one, okay? So let Sk be the first k things in this order, okay? So Sk is equal to I1, I2, up to Ik, such that phi I1 is greater or equal to phi I2. So this is the order in which we sorted. Phi In. So I'm just taking the first so many in this ordering. That's what we're doing. Does that make sense?
Phi 1.
Phi.
We're taking the first one.
I'm taking, so Sk, so, okay, maybe I didn't write this so well. Okay, let me write one more step. I think it'll become clearer. So this was the example. In green is the example, okay? So what we are actually doing is we are saying phi I1 is greater or equal to phi I2 is greater or equal to phi In. Okay? So the I1, I2, In are the different indices that are in the coordinates, and I just sorted like that, okay? So let's do that. And then the second piece is to take Sk to be the first k things in the first k indices in this order. So I1, I2, up to Ik. Okay, so you do this for all k. So k from 1 up to n minus 1. Okay, so I start getting sets. So let's do the example again. So S1 in the example is going to be just 1, the index 1, right? Because that was this index 1, it's the top one. And then S2 is going to be 1 and 6. Yes? And then S3 is going to be what? 1, 6, and 3. And so on. Okay? So we produce a series of S's. Is that S in here? The one from the easy algorithm. Will we catch it as one of these S's? Yes, right? So at some point it goes from positive to negative. So we will definitely get that one from the easy algorithm in this process, right? But here we're very ambitious, so we're going to do like n of these sets, so n minus 1 of these sets, and then output the one that has the smallest value of phi of s. Okay? So instead of looking at exponentially many s's, which are all possible proper subsets, we look at only n sets, or n minus 1 sets, right? I look at the Fiedler vector as my guide, and then sort it first, and then take the first and the second, first, second, and third, blah, blah, blah. But I only have a linear number of these sets, right? And then among these, output the best one in terms of phi of s. So the last piece of the algorithm is part 3 is output the min phi of sk.
Q of chi is.
Huh? Sorry?
Q of chi is. Q of chi sk. Minimum over the Q value, right?
No, minimum over this value, this value.
That's the same as Q of chi.
Oh yeah, it's the same, that is the same as Q of chi-s, correct. Okay, so this is the second algorithm. And then let's end with the theorem, and then when we come back we can see why it's true. So theorem is, okay, so let me erase this bit. Actually, let's put the theorem here because we'll come back to this. So the theorem is this algorithm will produce a cut that is like this. So theorem is that the second algorithm, algorithm 2, produces a cut such that lambda 2 is less or equal to phi of s, less or equal to 4 times the square root of the degree of the graph times lambda 2, I think. Yes. Not phi of s, phi of g. So this is the best that we can do, right? Phi of g. Phi of g is the minimum over all the phi of s's. This is what we're looking for, right? The best phi of s. So this quantity, which took exponential amount of work, the way we were looking at it here, that's an algorithm that's only checking n things, so n minus 1 things.
But nothing here depends on the cut. Nothing here depends on the cut.
Oh, I'm saying that whatever is the best thing there, the best cut there will, did I say this right?
That should be n over there, n lambda 2, right? It should be n lambda 2.
Okay, let me say this. This is correct what I wrote, but I think we need to, let me write the full version. I tried to write a short version. So the algorithm produces a cut of density less or equal to 4 times the square root of the degree times lambda 2. This is one statement, okay? So that algorithm produces, the best cut you get there will have this bound on the density, okay? But then separately, let's write the statement separately. So this, of course, implies that the best, like phi of g, is less or equal to this. Do you agree?
Yes.
Because here's a cut whose density is less than this, so the best cut is even better, right? Even lower. So this implies this bound. Good? Yeah? And then the second piece is that lambda 2 is actually less than phi of g. That's separate, okay? Separate.
What is d there?
Degree of the graph. So the max degree of the graph. So it doesn't have to be a regular graph, but there's a max degree. So at the end of the day, if you combine these two together, we will get that lambda 2 is less or equal to phi of g is less or equal to 4 times the square root of d max times lambda 2. Okay? So the message at the end of the day is lambda 2 controls the sparsest cut. So the bigger lambda 2, the bigger phi of g is. That means it's more connected, more and more connected, harder to make small cuts, right? But the algorithm we're going to prove is, we're going to prove this part when we come back, and this part is for everybody who's feeling very ambitious tonight. Okay?